Hi friends, today we study the AC analysis of a small signal amplifier. So this is a small signal amplifier circuit. So in the previous video we discussed about the DC analysis of a small signal amplifier. So here we study the AC analysis of a small signal amplifier. So this amplifier works both AC and DC sources. You can see here. So the red arrows indicates the DC current and green arrow indicates this one indicates the AC current. So here this figure shows the amplifier is working or this amplifier uses both AC and DC sources. So next, AC equivalent circuit. So in AC equivalent circuit we made two differences in the circuit. So first one is coupling capacitor act as a short circuit for AC signal. Coupling capacitors, so these capacitors C in and here there is a capacitor like this. So this is C out. These capacitors act as a coupling capacitors. So this coupling capacitor for AC signal act as a short circuit. So we already tell the working of the coupling capacitor in the small signal amplifier. So another is DC source can be removed and it is connected to ground. So here there is a DC source. So here there is a DC source is connected to. So DC sources can be removed and it is connected to ground. So after these changes we get this type of circuit. So this is a small signal amplifier. So it is a AC equivalent circuit. This is the AC equivalent circuit. So in this circuit we have only AC sources. There is no DC sources. There is no DC sources here. So these DC sources here and here is connected to ground. Next, and also the coupling capacitor is present here. So this coupling capacitor behaves as a short circuit for the AC signal. So next, AC load line. So this circuit is helpful to study the AC load line. Okay. So AC load line. So AC load line can be drawn in the output characteristics of a transistor. So here we use CE means common emitter configuration. So the output characteristics, the output is in the collector and emitter junction we get the output. Collector and emitter junction we get the output. Okay. So here we take only output of the small signal amplifier in AC equivalent circuit. So this is the output junction of the small signal amplifier. So in the output we have only two resistors, RC and RL. So this RC and RL is parallel. So here we calculate the effective resistance of these network. The effective resistance is given by, so these resistors is in parallel connection. So RAC is the effective resistance. RAC is equal to RC parallel. RC parallel RL. So you know how to calculate the effective resistance in parallel combination. Next, here this is IC collector current, and this is IB base current, and this is IE emitter current. So this IC means collector current is flows through the resistor, effective resistance RAC. So here we use KVL in the output of the small signal amplifier. So from KVL we have IC RAC minus VCE is equal to 0. So VCE is the voltage across the collector and emitter terminal. So here collector and emitter terminal VCE, and voltage drop across the effective resistance RAC is IC times RAC. Then KVL is equal to IC RAC minus VCE is equal to 0. So when no signal is applied, IC and VC are collector emitter voltage. So there is there is no signal means the AC signal or AC sources is in 0, or uh, it is not connected. AC sources is not connected to small signal amplifier. So in that case, IC is the collector current and VCE is the voltage across the collector and emitter. Next, but when signal is present, it causes change in the IC and VCE. So when there is a AC signal is present in the circuit, the IC is changes and VCE is also changes. Both these quantities are the changes with the AC signal. Okay. Next, maximum collector current due to signal is IC. Maximum collector current is IC. Maximum positive swing of AC collector emitter voltage is RC times RAC. Maximum AC collector emitter voltage means VCE is equal to IC times RAC. You can see here. Here VCE is equal to IC times RAC. Okay. Total maximum collector emitter voltage is, so here VCE is voltage across the collector and emitter terminal. It is changes to VCE plus IC times RAC. So there is no signal means AC source is absent. So VCE, just we have VCE. When AC signal is present, the voltage across collector emitter terminal becomes VCE plus IC RAC. So this is called maximum collector emitter voltage. Next, maximum positive swing of collector current is, so we get the relation here, IC is equal to VCE by RAC. So here there is no signal, no signal, so we have just IC. When signal is present, so IC changes to IC plus VCE by RAC. So this is called total or maximum collector current. So this one. So when AC is present, the collector current becomes VCE by RAC. So there is no AC, there is no AC. So this maximum change becomes to 0. Similarly, when AC is present, VCE becomes VCE plus IC times RAC. When AC is absent, so VCE is just VCE. Okay, so using these connections, we have a straight line equation. So this is the straight line equation. So this graph is made by IC versus VCE. So IC along y axis and VC along x axis. So here the collector current is changes to IC plus VCE by RAC, and VCE is changes to VCE plus IC RAC. So this is changes. This graph is change. This graph is called AC load line. This graph is called AC load line. So I already discussed what is load line, what is DC load line. So this AC and DC load line tells the variations of IC and VCE in the transistor. So next, so this is the graph of AC and DC load line. Graph of AC and DC load line. So both AC DC load line can be right in the single graph. Here this is the DC load line, and this is the AC load line. So both AC load line and DC load line is combined at the Q point, means active point. Q point. The collector current due to AC is greater than the DC load line. The saturation point here is greater than the DC load line, and here the cutoff region, the VCE voltage across the collector and emitter junction is less in the AC load line. So this is about the AC and DC load line for a small signal amplifier. Okay, thank you.